Guys, this is video 13.4. We're going to be talking about potential energy diagrams today. Something that you will be asked to either label or draw. I think last year on the Regents I saw that it was a question like draw the potential energy diagram for the following reaction, and you've got to be able to know what to do with the information that they give you. So let's kind of jump right into some more terminology. Activation energy. This is the, if you think about it, activation energy. So energy, activate, right? So it's the energy that is needed to get a reaction started, and I ran out of room, or to form what's called the activated complex. Okay, and we're going to talk more about activated complex and stuff a little bit later on when we get into the graphs themselves. So to form that activated complex of a reaction, so it's over the hill, right? So just like in a roller coaster, you need to put energy into the system to be able to go throughout the rest of it. So that first hill on a roller coaster is typically the slowest, where you've got to climb and climb and climb, and then you get to the top, and then you go fast through the rest of it. Same idea here with a reaction, okay? So we talked in the last video about exothermic reactions and endothermic and their heats of reaction. So now we're going to see what they look like visually in terms of a graph, okay? So we know that exothermic reactions do what with energy? They release, and I can't spell today, they release energy and they move to a lower energy state, okay? This is why they're the most common type of reactions, because less energy has to be put in, okay? That's the key there, right? Atoms, particles, reactions, guys, they're all lazy. We've talked about it throughout the year. Just like we are as humans, you know, would you rather run a marathon or stay in bed? Overwhelming majority, 99.9% would say, hey, I'm going to stay in bed versus run a marathon, okay? Same idea here, right? They want to put in the least amount of energy to get the reaction to go. So exothermic reactions happen much more frequently, all right? Much more spontaneous as well. That's another key word to kind of think about, spontaneous, okay? Doesn't mean that all of them are spontaneous, but they tend to be, where they will just kind of happen on their own to get to that lower energy state, okay? So it takes lower activation energy. So less energy needs to be put in. So when we take a look at a graph, these potential energy diagrams, this is what an exothermic reaction would look like. Okay? Where you start higher, your energy that you start with is higher than where you end up. You end up lower. Okay? So that's one of the biggest things to remember. So if we look at this in terms of the reaction pathway, that means this part right here is where our reactants would be, and this is where our products would be. So that, again, the products end up lower in energy than where you start with your reactants. Excuse me. So the hill that we kind of were talking about, this activated complex, is at the very peak point. Okay, it's the toppest part. It's the topmost part of your reaction. This is that activated complex. Once you get to the activated complex, the rest of the reaction goes pretty quickly. This is where like your rate determining step might be found. It's kind of in here, right? That slowest step of the reaction. You got to kind of get to that point before the rest can kind of go to the end of the reaction. So there's other parts that we're going to label here. One of the big things, and I'm going to kind of color coordinate it. You don't need to necessarily if you don't want to, but I'm going to do it because I think it's going to help many of you guys remember it since it's early on with this. We're going to kind of talk about different parts that are above the graph and then below the graph in terms of the line. So the line obviously is the black line. Anything that's below it means potential energy. It's how much energy is stored in that part of the reaction. So if we take a look here and I draw an arrow like so, this is my potential energy of the reactants. This is how much energy the reactants have stored within it to be able to go and be used or released or transformed within a reaction. The other term you might see, guys, is latent energy. That just means the same thing as potential. Okay, it's another fancy word for potential energy. So if I take a look here at this part, okay? This is going to be my potential or latent energy of my activated complex. So don't make it more complicated than it needs to be. Just remember that anything that I'm writing in purple is your potential energy. Okay, anything below the graph represents potential energy. So when you get and do some practice, you may have to label certain parts like, okay, where's this part on the graph, or where's this part? So where's the potential energy of the activated complex? It would be this line that you might have below it, or if it's labeled with a letter or something like that. And then, as you might think, over here, this is your potential energy of what? Your products. Okay, so that's kind of one thing to kind of remember is, hey, potential energy is below the curve. Okay, now other important pieces. All right, one of the most important, it's going to be kind of in the same area. This really should be going to the very top. This part right here, guys, notice where it is. If I can move it along, notice how these dotted lines are in here. I encourage my students every year, if you don't have these dotted lines drawn in there, draw them in there. Okay, you're going to see your practice sheet, they're not in there. But this may make it easier for you to see kind of those pieces. I can move this red arrow anywhere along here, wherever I want to. Notice it's the same distance, okay? Well, what distance is that? If I take a look, no matter where it is along those dotted lines, it's the distance from my reactants to my activated complex, okay? And if we're looking at it, since it's in terms of the reactants, that's going to be my activation energy, okay? That's my activation energy. It's how much energy needs to be put into the system to get it to go, okay? And this is symbolized with E sub A. Why it's oh my gosh, I can't even think. Why it's abbreviated that way, honestly, I don't know. All right, but it just is. Energy of activation is what I've always assumed, okay? Activation energy. All right, so it doesn't matter where you see those lines like that arrow, guys, the red ones, it can be moved along anywhere along that point, but it's still from the reactants to the top of that activated complex. Therefore, it's your activation energy. Okay, just like any of the other arrows I've drawn could be anywhere along this graph, okay, but as long as you see where they're pointing to, the very top point and the bottom point, that's what you're looking at there. Okay, then I'm going to do in green another term. And again, this is one that we could move anywhere along here. So it could be here. It could be all the way over here at the beginning. Okay, now I know I just said, hey, anything below the line, right, below that black line is your potential energy. But notice, guys, this green line, the first one I drew over here wasn't below it completely. Okay, so this one's a little bit different. Notice what two lines it's between. It's right here with the reactants and the products. This is your delta H. Okay, which is your heat of reaction. It's the heat of the products minus the heat of the reactants. Okay, so it's that difference between the two, which is how much energy is associated with the reaction. Either you had to put that much total energy or net energy into the reaction, or that's how much energy was released. Now, one thing I want to point out as well is notice all of this above is how much energy is associated with the reaction. But this activation energy, yeah, you put the activation energy in, but you then get it back out. Okay, so notice how the net, we talked about net ionic equations, kind of what's in there, like your net paycheck, right, is how much you actually take home, even though you have this thing called gross. The net energy is your delta H, but the gross energy associated with the system includes that activation energy. So you got to put it in at the beginning, but you're going to recoup that in the end. And then in this case, with an exothermic reaction, you also get back more energy than what you put into it because it's exothermic. It's releasing it. Okay? So let's take a look now at the opposite type of reaction, which is an endothermic reaction. So if exothermic release energy, what do endothermics do? They absorb or gain. Okay, so kind of just to go back really quick, we can see, guys, again, exothermic, because this net piece right here, all that's right in here, this part, that's what is released. That's how we can see that, hey, it's exothermic, because that's extra energy we're getting back that we didn't put into it. All right, so endothermic absorb or gain energy and move to a higher energy state. All right, that means more activation energy is needed. All right, that's the key that you need to remember here, is more activation energy is needed. This is why these are not spontaneous. They're not as common because energy must be put in to get the reaction started, which means you need a greater amount of energy to get it activated, okay? So we're going to say non-spontaneous. All right? So, same thing. Endothermic. We're going to kind of go through and label the parts. If you think, hey, I kind of know these parts, I think I can do this on my own, I would encourage you to pause the video and try to label those same type of pieces. It may look a little bit different, but it's still the same. Really, it's just now, hey, instead of going in the forward direction, we're in the reverse direction. So one thing, like I said, if dotted lines, guys, aren't drawn in there, draw them in there, okay? It's going to be a helpful tool for you. So pause it if you want to try it on your own. Otherwise, I'm going to kind of go through and label it as well here. So now these are my reactants. These would be my products. First things to kind of, get taken care of. This dot in the middle is my activated complex. Notice this difference here, guys, right? Look how much energy we had to put into the system to be able to get to that activated complex. This is like a really big roller coaster that takes like 30 seconds to get to the top because there's so much energy that's needed to kind of get it to go. Okay? So those are kind of the big pieces there to kind of start things. Now we can start filling in. So I kind of like to say, hey, this is my PE or latent energy of my reactants. This is my potential energy of my products. This right here is going to be my potential energy of the activated complex. Okay, that kind of takes care of all my potential pieces. So now I'm going to kind of go to the top parts. We'll take a look here, right? Notice what I'm doing. This is from my reactants to the uppermost part, which is my activated complex. So what's that going to be called? This is my activation energy. Okay, activation energy, or EA. Okay, again, I could move this over here. It could be over there. They're not going to probably do that, but I just want you guys to be aware that you could see that. It could be anywhere along there. Now, the other part that I need to do is my delta H, okay, my heat of reaction, my enthalpy. And again, that could be over here. The big thing, guys, is that it's between the products and the reactants. Now notice, we put in all this energy for the activation energy, all this stuff. We only got a little bit back. We still had to put in a lot more than what we ended up with getting back, okay? So notice a couple of things that are interesting. Every reaction is going to give some energy back, but we're looking at the overall piece of it to where, hey, what's the net amount? And so we had to put energy into the system in the net phase versus getting it out in the net phase, like the exothermic. Okay, make sure you guys know these parts to these graphs. I guarantee you will see one. Make sure you know that endothermic. All right, if you were asked to draw it on a test or a quiz, endothermic looks like that. That's what you would draw in there. Exothermic would look something like this. It doesn't really matter how nice it is. You just got to make sure that, hey, exothermic, you end up lower than where you started. Endothermic, you end up higher than where you started. Okay. Now, the last thing we're going to talk about here with these potential energy diagrams is how exactly does a catalyst shorten the reaction time needed for the reaction to complete. And we talked about this is one of the 6 factors that speeds up a reaction or affects the rate of reaction, and it's a catalyst, right? So here's what happens, guys. Without an enzyme, aka catalyst, right? Because enzymes, if you remember from biology, are catalysts. Right? The red line is what it would look like. But with a catalyst, notice this is what changes. So what does it change, right? It lowers the amount of energy that's needed. So notice the activation energy with the enzyme versus the activation energy without. That's what allows it. This is that different pathway that it can take. So a reaction could take the red line, well, that's a longer way, or it could take the blue line. 2 different pathways. So the thing to remember, guys, with a catalyst, and I have seen questions, old Regents questions dealing with this, how does a catalyst shorten a reaction? Well, the activated complex is lowered, or the activation energy is decreased, or the reaction pathway is shortened. It could be any one of those three. We don't actually know, scientists today don't know which one it is. It could be any one of those three how a catalyst works. There's a lot of research being done still on catalysts. We know that they speed up reactions, but we don't know exactly their exact mechanisms all the time. All right, but it could be one of those three things. Make sure that you know these three outcomes, because you very well could be asked a question about these come June. All right, so until next time, I will see you guys later.